Awesome. Thank you so much for the introduction. Yeah, no, and before I went to Stanford, I was at UW with Dan and Magda. For those of you who know them, also doing databases work. So it's really great to be chatting with you guys again. Yeah, so just as Emmanuel mentioned, my talk's going to really have two parts today. Really talking about some work that I've been doing over the last year and a half time frame. And the first part's really going to dive into this notion of foundation models, also called big models. I'm going to talk, give a high level overview of what these are and really focus on why these models are so important and are really changing the way in which we're building and developing applications and systems. And in particular, I'll introduce a couple of interesting challenges that I think are pretty relevant for the data management community with managing and maintaining those models. In the second part, I'm going to dive into some really fresh off the press work that was just submitted to VLDB a couple of weeks ago on actually this notion of incremental maintenance of some of these models, which I'm also very excited about. And also, if there are any questions during the talk, feel free to ask them. I also know there's some time at the end, so whatever is easiest for you folks. Okay, so without further ado, I'm going to start with this notion in diving into foundation models. Okay, so over the past 2 years, we've really seen this trend in what I'm calling bigger is better models, where we've seen that the model size has really been rapidly increasing. And so on the left is kind of this common plot that you see in slides like this, where you have the number of model parameters on the y-axis and time is on the x-axis, and you're really just seeing this exponential growth in model size over time. And even now, there are discussions and hints of companies and organizations training even bigger models than are on the slide right here. Now, with this shift in model size, you're seeing terms come into the news like the term foundation model, data centric AI, emergent behavior. And so I want to sort of tease apart what some of these terms mean and how they're all related to this trend in bigger is better models. Slide. Wait. Oh, no, sorry. I lost my mouse for a second. Here we go. Come back. Nope, wrong direction. I guess I'll take it. There we go. Okay. Right. So I'm going to give sort of the classic example of a foundation model for those of you who may be unfamiliar. But this one sort of was all over at least the machine learning news cycle for a while. And this is the model GPT-3. It was trained by OpenAI in collaboration with Microsoft, I believe. And at the time it was trained was about 10 times larger than any other model trained at the time, approximately. And this model was trained over about 40 terabytes of text, took about a month to train on 1,000 GPUs. And according to the very trustworthy source that is Reddit, somebody said it estimated took about $4 million. I don't know how true that is, but a lot of money, right? So a lot of impressive engineering took to get a model to be trained at this size. And they've obviously sort of publicly released an API to this model, so people have been able to explore it. And so this was, again, incredible engineering feat to get a model at this size to train. But was also really interesting and exciting was the behavior that this large model showed to users. And this was really one of the first models to show what researchers are calling emergent behavior or in-context learning. And that's the ability for a model to recognize a pattern and follow it without any weight updates or fine-tuning. And so how this works with GPT-3, I have some examples on the slide here, is it's all through prompting. And so GPT-3 is a language model, so you give it some text, and then you ask it to basically generate more text conditioned on the prompt that you gave it. And so here they were actually conditioning the model with input-output example pairs and having it continue that pattern. And so on the left, they would give it input-output pairs of translation, so going from English to French, and then would say, hey, like, what's the translation of cheese, of the word cheese into French? And incredibly, the model could figure out how to do this without having to train a model to do translation, right? And there's been ton of work in how do I train translation models, and it was able to do it out of the box simply with giving it examples. And on the right, we have something a little more near and dear to our hearts, which is taking an example query and turning it into a SQL query, with the prompt being an instruction of what they wanted the model to do, and potentially some input-output example pairs as well. And so this was sort of mind-boggling to researchers when they first saw this, and is really sort of stepping near this idea of AGI, which was what got people really excited, because humans can learn this way. We can learn through examples, but up until this point, it was it was difficult in models to see this kind of behavior. And also GPT has had massive impact on industry as well. With a quick 2-minute Google search of startups dealing with GPT-3, here are 4 already. Companies that are again building tools for people on top of this interface that are again forming companies. Right now, they're all language-based for the most part, but we're seeing a lot of foundation models being built and constructed around images as well. So we'll obviously see this space expand and get more diverse as time goes on. Right, so I've sort of given you an example of foundation models and have sort of hinted at these terms like data centric. And I want to dive into for a second and really get at the heart of, in my opinion, what makes a foundation model a foundation model. And there are 2 aspects here. And the first is really on this slide, which is the idea of this self-supervision over large quantities of data. If you take a more formal definition of foundation model, on the first line, there's sort of 3 keywords here. That a foundation model is one that is trained in a self-supervised fashion, which here means there are no labeled data. No engineering has to go into labeling examples as to how you want the model to train. It's all naturally generated from text. And the most common example of this is language modeling, where you'll have a model predict a token in a sequence. And that label is sort of naturally there because you already have the sequence of text. So this is the no labeled data part. Oftentimes the data is broad, it's across heterogeneous data sets and different sources, and it's oftentimes trained at scale, which is just another word for saying it's really big. Now, one subtle point I'm going to add to this definition, which really isn't included in the formal one and isn't required, but that oftentimes foundation models are trained with these very standard black box homogeneous architectures. The transformer is probably one of the most prominent one. CNNs, you see a lot of models trained with that as well. So very standard architectures that are highly optimized. So you see a lot less tweaking of model components when you're training these models. Now, where does this give us? Where does this lead us? We have a ton of unlabeled data across a lot of sources being fed into a very standard architecture that engineers don't control as much. The implication of this is that the only way to really steer the model and control what it learns is going to be through the data itself. And you'll hear this term that these models are fed by their data. And this is where you're seeing this term data centric AI come back, is because the importance of data has now shifted because it's how we, for lack of a better word, control these models. Again, we can't tweak the architecture. I can't tweak the labels. I can't really tweak the loss function that much. It's all through the data. And I'm going to come back to this point in the next couple of slides as well. Now, the second thing in my mind that is really critical for this notion of foundation model is this idea of it being a backbone layer or a foundation layer. And this was actually one of the reasons why they're named foundation models, is to get at that idea that these models are purely meant as a foundational first layer that are then adapted to downstream tasks as well. And so this picture on the left was taken from the foundation model paper, showing some common use cases of this foundation model adaptation, looking at QA and sentiment analysis and some pretty standard NLP tasks. What's really exciting to me is that we're also seeing this notion of adaptation occur in the data management community. And we've seen a lot of exciting work in the last 3-ish years looking at how to apply this notion of foundation layer to tasks that the data management community cares about. We've seen a lot of success in data integration tasks like entity matching and entity linking, as well as some work from this lab doing database tuning, and also the work on neural databases, which is sort of thinking about how do I replace a database with a foundation model. And there's a lot of other work in the space as well. These are just sort of some of the four ones that came to my mind at first. And so again, this is even impacting our community as well. So really, these foundation models are changing the way in which we're building and interacting with our systems and our applications. And again, we see this focus again on the data, this notion of data-centric AI. But for those of you who are around in the pre-foundation model, sort of just the deep learning revolution that took off a few years ago, we've actually seen all this notion of data-centric AI before. It wasn't necessarily called that, but this idea that data is one of the most important factors for training a model is not actually new at all, right? We've seen this before. And when deep learning took off before foundation models, it also changed the way in which engineers built systems. They moved from these really rule-based heuristic pipelines to things that could be learned. And it became very clear at the time that one of the most important factors when building these deep learning models was going to be their data. They were very data hungry and needed a lot of supervised labeled data. And so a ton of work from our community and others were all built to help get that data, that labeled data, to the model. You see a lot of data labeling companies as well, which is what the picture is on, using crowd workers and data programming to help bring labeled data to these models. And so to really highlight what made that data revolution different from the one that we're seeing right now, here's sort of this pre-foundation, a simplified pre-foundation model pipeline. It really started with this idea of I want to build a task-specific downstream model. And so they started usually with task-specific data. This data was fairly large and had to be typically labeled either by hand or through some of this data labeling techniques and tools. A machine learning model was obviously trained on this data. Typically, the model was more customized in terms of the architecture, not always, but it was a little more custom for the task, and then was obviously deployed downstream. And so again, these models revolutionized systems, but they weren't perfect. They needed a lot of data still, and the data still had to be labeled. This made things fairly difficult to maintain because if I wanted to go and switch to a new locale and let's say train a model to do the same task in French, I'd have to go and rewrite all of my rules or redo my entire labeling pipeline. And also the customized architecture can be difficult to maintain in industry when you're having teams maintain a ton of different kind of smally, sort of minorly different models here. Now, what's really changed here with this foundation model pipeline is instead of starting from this task-specific data, you're starting from large corpuses of general knowledge that's again, completely unlabeled. Wikipedia, you see that, books, web pages. I mean, the GPT-3 model was trained on basically entire web. They scraped the web documents, as well as, again, you're seeing images as well. And so all this general knowledge is now being fed into this foundation model. And then this model is now adapted using this task-specific data to build that downstream system. Now, because of this starting out with a foundation layer, oftentimes you'll need less labeled data. It's kind of one of the benefits of transfer learning. And even further, oftentimes you get a downstream quality lift compared to that predecessor model simply because you're using this foundation model. So it's now making applications easier to develop. And again, a little less need for labeled data. And so again, data is just as important now as it was back then. It's just we're seeing a shift in the kinds of data and why the data is important. We're moving from how do I label massive quantities of data to having an increased focus on how do I get as much data as possible to feed to these models. Now, obviously, these models are also not perfect by any means, and there are a ton of challenges and opportunities with these models. There are, in fact, two sort of 200-page papers written about what are all of the challenges and opportunities with these models. The one on the left is from the Stanford community where they coined the term foundation model, and the one was released, I think, a couple of weeks ago, the one on the right from the Beijing Academy of AI, also talking about this idea of what they're calling big models, which is their term for foundation models. And for me, what I think is really interesting is where does the data management community come in? If these models are so driven by their data, it makes no sense to me that there isn't a place for management, for data management techniques and toolings and ideas to really play a role in how to manage these models. And so for the next 3 slides, I'm going to give sort of my take on 3 really interesting areas that the data management community can kind of get involved with these models, but this is by no means complete. So the first is this notion of integration. And data integration has been studied in our community for decades and is still a problem to this day in industry. Now, what we're seeing with these models is that they're increasingly being trained over more heterogeneous data sets. A model I worked on in the past called Bootleg was trained over text and structured data at the same time. And you're seeing some really exciting models, which are simply just fun to play with, that are trained a lot over text and images. Like DALL-E 2 was a model that was released really recently, and you feed it in a caption and it generates an image. And so here, this model, they fed the caption a teddy bear on a skateboard in Times Square, and the model generated that image for them. And I encourage you, their website has a lot of other fun examples of like one of them is like a dog with a nebula in its head. It's pretty wild that it can do this. But again, we're going to see models where you're hearing sort of talk about people training models over video as well now. And so pretty soon you're going to get models trained over really complex data sets, code, video, text, images. And from the data management side of things, we really need to be able to support integrating and managing this highly heterogeneous and multi-scaled and large-scale data sets here. Something else that's coming into play is this idea of privacy and provenance. There's a lot of questions around how do I take one of these general purpose models, apply it to my data, and how do I understand any of the privacy implications of that process? What if I fine tune it a little bit? What does it learn? How can I either understand privacy or at least nothing else, understand the provenance of my data and where my data is coming from? Especially if you're in industry and you're going to train a model over mixed public and private data sets, like it's very important that you maintain and understand where that data came from. And so all of this, I think, is a kind of a ripe field for data management to come in and play a role in helping manage this data. Now, the other one is going to be data management is going to be monitoring and data exploration. As these models are trained on data without labels, engineers oftentimes have a less understanding of the quality of their data and how that impacts downstream model performance. There was actually a really interesting paper which came out about a year ago, which was looking at how if all they did was take sort of a language corpus and remove duplicate sentences, their model trained faster and oftentimes with a little bit of a higher quality. And this was something as simple as a deduplication task that is kind of the bread and butter of the data management community. And they were showing that simple idea actually helped the model itself, which is just telling me that there's a lot that people don't understand about the quality of their data. And it's gonna be very hard for them to understand that because it's so high scale and heterogeneous. And so we're gonna need techniques to allow engineers to understand this data and also tie it back to the model performance. We've already seen some kind of exciting works like this, Robustness Gym as an NLP evaluation toolkit to try to help engineers understand their model. We've seen work from data management as well, like the work in Sliceline that appeared in SIGMOD this year, which was looking at how do I extract slices of data. And so all of this, I think, is stepping stones towards really getting at the idea of how do I apply this now to, again, more complex data sets and more complex model outputs, not just classification tasks. And so, again, another exciting area. Now, the last one, which is very near and dear to my heart, is this idea of patching and model maintenance. The models are actually treated fairly as static artifacts. There is actually this this API that you can get access to embeddings from this language model from OpenAI, and they have a disclaimer at the bottom of their webpage, which basically says, like, warning, our model is not trained after like October of 2021, so don't expect it to get anything right about the world that happened after October 2021. And I thought that was fascinating that they actually put a disclaimer about, hey, look, this thing is basically static, but the underlying world is not static. As facts and knowledge about the world change, these models are going to start making mistakes. And it's going to be increasingly important for engineers to have the ability to identify, like the last slide, and then importantly, correct the errors. And it becomes even more challenging with how do you correct a model that potentially you don't even own? Like if I see a mistake in GPT-3, what do I do about it? And I also believe that because these models, again, the data is so important here, data engineering tools are going to become this kind of key tool in an engineer's tool belt for fixing these things. Techniques like data augmentation, data programming are all, I think, going to come into play for how do you sort of continuously maintain and deploy these models. And so again, this is another area that I'm pretty excited about, and obviously it'll lead into that the second part of the talk. So I want to pause here and make sure there aren't any, and if there's any questions, like feel free to ask them now. Okay, well, without further ado, I guess I'll get started on the next the next part. I raised my hand and I thought I was asking a question. Anyway, the joys of Zoom. Okay, so I'm now going to talk about this recent project that I've been working on, which is really starting from that very last slide, which is the idea of model patching. So I did a little work on patching models where there's sort of a specific error case that we find, and then how do I sort of fine tune and correct the models? And it was an interesting problem, but it was a little hard to get the right angle on it. And sometimes when you have something that's too big of a challenge, it's hard to find the right foothold. And so, I ended up talking to a lot of people and trying to understand what was really a core challenge that was a nice sort of smaller problem that fit into something that I cared about, but was also kind of tractable. And so starting from this vague idea of patching, I ended up actually narrowing down the problem in two key ways. And then I'm going to talk about in more detail about what that sort of narrowing down means. And so the first is, instead of starting out with this big kind of broad notion of foundation model, I'm really going to limit it to entity embedding models. And these are models that I built an entity linking system, and so they're near and dear to me, and I kind of understand them a lot, and also know how they're used and the importance of entities in downstream tasks, right? Systems like Siri, your personal assistants, search, and QA all use entity representation. So it was a really useful sort of subclass of models to really look at. Now, instead of looking at kind of arbitrary errors, I was really considering the case of what if I just assume my data is being updated under the hood, and my goal is simply to update the model with respect to these data updates. So it's a little less an engineer finds an error and tries to correct it, and more just saying, hey, look, I have new data. How can I update my model such that it preserves all the updates to the data? And so again, instead of patching, I'm really going to be focusing on entity embedding models under this world of data updates. And so I'm going to talk more in detail about each of those. So I want to sort of give a high-level overview of entity embedding code and sort of what I want you to think about when I mention these things. And so there are two inputs to entity embedding models. And the first is a structured knowledge base, which I'm notating as KB at time t here. And simply, this is just a relationship of all of my entities and any structural metadata about that entity. And so, for example, I oftentimes use global knowledge, like from Wikipedia and Wikidata. And so in that, I have entities like David Beckham and Victoria Beckham. And David Beckham, for example, would have the type soccer player and a description maybe that he was a player for Manchester United. And you can imagine that this table is going to be really large and it's going to have a few million entities in it. Now, the next input is going to be a second table, which is going to be your unstructured data, which I'm notating as DT. Now, this is going to contain entity annotations that are sort of context associated with entities, and actually there are foreign keys that link back to your knowledge base. So if you think in Wikipedia, you can extract a sentence that's talking about how Beckham was one of the highest paid soccer players, and then you'll know that that mention of the word Beckham is actually a foreign key pointing to David Beckham. And so you have these two sort of basically joined relationships, the structured knowledge and this unstructured text. And these two inputs together are what get fed into the embedding model for training. This model is then going to sort of jointly learn over both of these inputs, and will basically, once it's trained, you in essence run an evaluation step and it spits out representations for every entity. So David Beckham's going to get an entity, Victoria Beckham will. And you could think of this as like a key value store, where the key is going to be the entity ID and the value will be the representation space or the representation. As I mentioned earlier, these embeddings are now all used in downstream systems like recommendation and QA. And there was a tutorial last year where I talked about kind of these embedded ecosystems for those folks who are curious. Now, I also want to pause it and just make sure I give a high-level overview of what these embeddings are going to learn and how they encode that information. I mean, this is a very high-level picture that I want you to keep in mind here. So embeddings encode information really all through the relative placement of one entity to another in some underlying embedding space. And so the representations are going to be placed relatively closer to each other based on if they have, for example, similar types or appear in similar contexts together. So here you may see that Roy Keane and David Beckham, they're both famous soccer players, are going to be near each other because, again, they're both soccer players. David and Victoria Beckham might be close to each other because they're married and oftentimes co-occur in sentences together. All the presidents may be near each other, again, because they're presidents. And so it's really this idea of an underlying embedding space and the relative distances that I want you to keep in mind. There's a ton of work in looking at this from a more theoretical lens. How do I probe embeddings to understand what they learn? So again, this is very high level, but just something to keep in the back of your head. So again, the takeaway from this is that basically the representations are going to code both structural information and related contextual patterns for an entity. And this is markedly different from our standard KG embeddings that really just look at structural data. So like node to vec style. These are really more, again, also trained over the context now. Okay, so that's for the entity embedding models. I'm now going to get into this idea of data updates and how I'm thinking about this. And so this is one of my favorite visualizations that I stumbled across this last year of somebody who is, I think the website is called Listening to Wikipedia. So somebody literally hooked a feed into the Wikipedia, they have like an RSS feed that gives every single update to Wikipedia in real time. And so here's like a short little video I took up this web page. And this one actually, like you can just go to it in real time and just watch this, which I have done more and wasted more minutes than I care to admit. And you can literally just see Wikipedia being updated in real time, where the size of the bubble is the size of the update. It's not exactly precise because here the updates can be to like talk pages or citations. So it's not necessarily a factual change of the world, but it's still getting at the fact that this data is being updated in real time, sort of as we speak. And there's about 80 updates per minute here, according to the website. And again, I just thought the graphic was really exciting. So as always, I'll share it whenever I have the excuse to. And so what's really challenging about this is that the fact that these challenges actually, the data updates are going to occur at different frequencies and cadences and at different sizes. So for example, relationships like where an entity works or who is the board of directors of a company is going to change very frequently within a day. And if I want to keep my downstream systems up to date, I'm going to have to update that underlying representation. If a user queried for who the board of directors of Twitter is, they obviously want the most recent information, especially as Elon Musk just joined a week ago, I think. I don't know. At some point, it was all over the news recently. Now, on the other end of the spectrum, we're going to have these large dumps of updates that occur as well. And this is a snapshot of the Wikidata sort of dump reference page. And you see that dumps occur about every month, and there are these large dumps with a bunch of new entities, as well as updates to old entities as well. And these arrive less frequently. And so the whole challenge here is that I need my downstream systems to reflect these data changes, right? Like I needed them to preserve this information, but I have to be able to do it at all the different cadences that the model can that actually occur in the data updates. And so how I'm actually going to model this is I have my knowledge base at time t and my unstructured data at time t. At time t+1, I assume you can have updated entities. So for example, at one point, David Beckham obviously stopped being a soccer player and among other things is an ambassador to UNICEF. So maybe his type will change as well as his description. And then I also am going to allow for new entities to arrive, such as new entities to your knowledge base and newly added context that have foreign keys pointing to my KB at time t+1, and also refer to entities from before as well. And we also talk in the paper about what do you do about deletions, but for the simplicity of the talk, I'm just going to focus on updates and new entities here. Now, if you sort of sniff at this problem, it's actually very similar to one that we've seen before in the data management community. And that's actually just the relational view maintenance. And so I'm going to give a very sort of kindergarten version of relational view maintenance, and I'm going to map it to this problem of entity embedding view maintenance. So when you're dealing with relational views, you often start with some view definition, which is typically a query over some base relation. Obviously, you can have multiple relations and the query can be arbitrarily complex, but for now, let's just pretend it's a single relation of queries. Then at time t+1, you assume some delta over your data, delta data comes in, and your whole goal is how can I compute my view at time t+1 to reflect those data changes. Sometimes you have to recompute the view fully and pay some costs, usually proportional to the size of the relation. Again, I'm simplifying things here. But oftentimes, again, there's a lot of work in our community about how do I do this more efficiently, but still preserve the definition of the view. Now I'm going to do something very similar in this entity embedding problem. But here, instead of one view, I'm actually going to have two views. My first view is actually going to be the embedding model itself, that black box that I had on the slide earlier. And here, the embedding model is going to be trained over all my input data sets, my DT and my KB of T. Now, for machine learning, oftentimes you start with an initial model, which here I'm notating as in not. You can think of this as just random initialization parameters. It's not super important, but it comes back when you think about fine-tuning models. And so in essence, that's my first view definition. And just like relational view definitions, I'm training it over my base relations here. My embedding view, ET, is simply going to be evaluating my view, my model view, over the knowledge base to generate my entity embeddings. Now, again, just like with the relational data, I'm assuming some notion of data updates. I'm assuming I can get some delta context data as well as some delta structure data. Where here, the delta KB is consisting of new and updated entities. And then my whole goal is to recompute my model and my entity embeddings at time t+1, where again, I'm going to pay some cost. Now, I'm actually going to dive into the bottom right part here about the recomputation and sort of explore what this is doing here. So I'm going to assume that just like with relational view maintenance, that if I fully recompute my model and my entity embeddings at time t+1, it's going to be the most accurate update and the one that faithfully is going to respect all data updates without sort of forgetting any old information. In other words, this is the gold standard computation that I would like to match in anything that I do. Now, in a perfect world, you would just recompute this every single time. But as Emmanuel mentioned at the very beginning, this is very expensive. The cost of this two-view computation is going to be the cost of training the model, which is that first term on the left, which is usually proportional to the size of your context data. The knowledge base comes in terms of training, potentially in terms of convergence, but just for simplicity, I modeled it as a cost times your context data. Now, the cost of generating embeddings is typically the cost of basically running evaluation on your model over your knowledge base. And the huge challenge here is that term on the left is exponentially expensive. That's the thing that takes days to weeks to train. And even bootleg itself, that entity embedding model took a week to train. And so again, you're at this point where this cost is so expensive that you cannot in any way keep up with with the different update frequencies. Even with the slow dumps that occur every month, you're going to struggle a little bit to keep up. And so the whole problem is, how do you avoid this high cost when you're recomputing the view? Now, you might say to yourself, well, wait a second, in data management, what we do is we do incremental updates, right? You incrementally maintain the view, and you can sort of do tricks that rely on certain statistical properties of your view definition in order to incrementally update this view. Now, the one challenge is that it's not readily clear what are incremental updates for a model. And in particular, since it's basically it's a black box. And so I don't really understand, I can't have any guarantees about how do I update a model incrementally. But we're still going to show a couple straightforward update approaches, and let's just see how models perform. I know that there aren't any nice statistical properties, but there might be something going on that we can take advantage of in trying to solve this problem. Okay, so I'm now going to present three incremental sort of strategies that are fairly straightforward if you just look at the definitions of the model, the training of the model, and the evaluation step. And just like with relational incremental updates, you kind of will swapping inputs with the delta inputs. We're going to basically do the same thing here. And the whole goal, again, is to save on cost. Now, the first update method is basically the lazy update method. It's where I don't do anything. I'm calling it cache incremental to give it a slightly more formal name, but it's basically the lazy do nothing version. And what this means is, in essence, I'm not going to train my model at all. I'm simply going to update it to respect any new entities. That might mean adding new embeddings to my model. And then I'm simply just going to evaluate my model on my new entities that are in the delta KB, and then simply add those to my embedding matrix. And when I have this evaluation on a delta KB, I want you to literally think of this as like a hot swap copy operation. So I literally copy my embeddings from time t to t+1, and then just update the rows for the delta KB entities. Now, you might think this is a poor quality update, and it turns out it does have some problems. But I really want to keep this one in because this is actually fairly standard practice in recommender systems already. It's oftentimes called the cold start problem, and it's when you don't always have enough information about your delta entities to really learn anything. And so there's a whole line of work at actually how do I basically make cached incremental updates more efficient or more highly performant. And so I wanted to make sure I included this because this is actually something that they do in industry, and it really relies on a model zero-shot performance. Now, the next one is where I am actually going to update the model. I'm calling this one context incremental because I am updating it on incremental context data D. But I'm keeping the entire knowledge base here. So I'm going to evaluate and generate a representation for every single entity after I update it only on my incremental context data. And the last one we're going to look at is what I'm calling fully incremental, where we're going to be incremental both in the context data and in my structured knowledge base KB. Now, you might be wondering, why don't I make things just incremental in the KB? You could, but you're not really going to get any cost savings. Again, the real cost is looking at that. The real cost of this update is the size of your data, your context data D. And so you're really after, how can I decrease the size of my context data? And then ideally, you'd also like to make it incremental in your entities too, because it lets you kind of have this nice little copy operation, which is also more efficient. So these are the three update methods that we're going to look at. And our whole goal is to say, hey, look, let's just try what's straightforward, understand their performance, and see if models maybe have some properties that would let these incremental update methods maintain performance compared to the retrained model. And so again, my goal is to match retrained performance in all of this. Okay, so we actually obviously we ran this to see how the performance is doing. And so here what I ended up doing is I built my own Wikipedia data set that was looking at two different snapshots over time. And so I had some naturally occurring updates and changes to my entities. I looked at two different styles of entity embedding models and compared their performance on a downstream entity linking task where I was measuring how well they performed compared to a retrained model, which is what the y-axis is looking at. The model on the left, I'm calling simple NED because it's a very simple model to develop. Basically, each entity gets its own embedding in an embedding matrix, and I literally just update that embedding over training. It's a little similar to kind of word to vec style, although how you add the context is through a transformer, and so it's a little more complex than that. But you can think of that at a high level. It's basically learning this embedding matrix. The model on the right is the one that I built earlier, and in essence, it's an encoder style architecture with a transformer. So you end up serializing an entity, you turn it into text, and so you give things like its description and its types, and then you, in essence, feed it into BERT, and it spits out a representation at the end. I can talk more details about the model if folks are curious, but it's two different styles of embedding models, and the one on the left is typically what you see with more state-of-the-art embedding models. Excuse me, the one on the right, and then the one on the left is sort of a simpler model that was pretty common a couple of years ago. And then lastly, for this experiment, to keep this ablation a little cleaner, I'm only assuming you have new entities added and just removing the complexities of updates. And I'm having a hard separation of my delta data. So my delta D here is basically only going to contain delta entities. So it's kind of this nice kind of incremental setup in terms of the data. So my new data comes in and it's only talking about all the new entities. Okay, so now to actually go into the takeaways of this experiment, we're looking at performance of kind of old and new entities. And again, our goal is to maintain performance across the board. And what you see pretty clearly is that the cached model, in particular for that simple NED, is really struggling and is basically near random performance on new entities, which makes a lot of sense. It's getting basically a random representation for those entities. And so it's not, it has no information to leverage to actually perform the task. And so you're seeing a kind of catastrophic failure there. For any of the methods that we actually do an update, we're also seeing some problems where the context incremental model is struggling on these old entities, and the full incremental model is actually struggling more on new entities. And neither of them across the board are going to maintain the performance of the retrained model. I'm going to talk about why this is in the next slide. And one thing, though, that is promising is that you are seeing some speed ups here. The cache incremental model obviously has about 100 times speed up because you're not training anything. And the context in full here in this experiment were about 3x faster. And again, the speed up here is really going to be the ratio of your DT data or DT plus 1 data versus your delta data. So obviously the smaller the update, the smaller your context data, the faster the update's going to be. So I now want to talk about why we're seeing this performance degradation, especially in these models that we're updating. We want to update our model to maintain this information. And so we need to understand why these context and full incremental models are not able to maintain performance. I'm going to explain this problem through the lens of embedding distortion. And embedding distortion is simply saying, hey, look, if I have a retrained model, I have some truth about where I want my entities to basically be placed relative to each other in some embedding space. I can then measure an idea of how far apart entities are in an update method versus the retrain method. So it's looking basically at how embedding distances are distorted in my updated model compared to my retrained model. And so I'm going to try to show this pictorially. I think it's an easier concept to understand with pictures rather than numbers. So I'm going to try my best to do that here. So on the left, I have a very simple diagram of how I want you to think of embedding models and if entities being trained and updated. On the left, you have an orange embedding space, which is representing where my entities are at time t. And here I'm using circles to be my old unchanged entities, and triangles are my new entities. And then at time t plus 1, my circles get updated, and then my triangles get added and placed as well. And you start to see little clusters form. Maybe they're all soccer players, they're all presidents, but they're all sort of updated and moved, and then now kind of faithfully live in this blue embedding space. Now, what happens when I have a context incremental model, for example, and a similar thing is true for the full incremental model, you're seeing a little bit of a different behavior here. Now, again, my context incremental model is basically just trained on triangles. And so what you do see is that relationships between triangles are actually fairly well preserved, right? Again, both models see all of the triangle data, and so are kind of able to learn the right patterns, right? If 2 new soccer players are added, the models can learn that, like, hey, look, these are both soccer players, they should probably be close to each other. Now, likewise, circles, for the most part, at least the context model, aren't really updated much in training. It's not learning anything new about them. And so some of those relationships are preserved as well. There is some drift, and it can lose performance over the circles, but it's a little better able to maintain that kind of relative information because, again, it's not seeing them frequently enough in training to kind of learn anything new about them and cause them to fundamentally change those relationships. Now, really what's going to be going on is when you start looking at relationships between triangles and circles. Because again, the retrained model was able to see triangles and circles together at training. And so it was able to learn that these things maybe should be relatively close to each other or far apart. Now, my context model didn't see that. It didn't have a notion of how triangles and circles are related to each other. And so those relationships, you have no guarantee about how it's going to learn them. And that's really where you see the distortion. And you end up seeing, again, like a larger distortion when you start looking at triangles versus circles versus sort of entities of the same type. So this is a little bit of a hand wavy figure, but it's getting at this idea of that the updates need to be able to maintain these relationships across triangles and circles as much as it does between all the circles and all the triangles. And so the whole goal in this project was, how do I actually prevent some of this distortion or mitigate it in the model? And so in this work, we actually, one of the update methods is what I'm talking about here is this notion of alignment. And so our idea was like, hey, look, we have these 2 embedding spaces. We have this orange space and we have this blue space. So why don't I just choose the orange space and try to fit everything in that space in a way that lets the triangles learn where the circles are placed. And so what we end up doing here is basically we're adding this alignment term that's forcing the model to basically keep the orange embedding space as the space that it's going to learn on. And so in essence, what you do during training is that I mentioned before that the circles aren't really seen in training. Well, they're oftentimes actually seen frequently as negative examples if you know how certain styles of training work. So they're seen not so much as positives. You're not learning a lot of new relationships, but they are seen during training in sort of a negative context or as negative examples. And so what you can do is you can say, hey, model, while you're training, place the triangles wherever you want. But whenever you see a circle, I'm going to encourage you to keep it exactly where it is and maintain the space that all those circles are on right now. Again, you can actually enforce this through like a simple L2 regularization, which is what our alignment does. And in essence, you're getting the model to place the triangles where the circles already are, rather than letting them kind of move up completely freely and learn whatever they want. So in essence, I'm forcing the model to maintain that orange space while it's being updated. So in the work, we also discuss a second update approach where I in essence choose the blue space and then try to sort of smartly update the model to reflect the blue space of updates. For time, I'm not going to talk about that here, although I will give a little teaser as to the results, because a lot of the work was understanding the trade-off between these two different update methods. Okay, so the overall framework here is you start with all these data and model artifacts at time t+1. You have your models trained at time t and your entity representations, and then you have your delta data come in at time t+1. Our first step is we then now update our model on our incremental data using this alignment loss now to generate an m hat at t+1. And then we do that hot copy operation on the embeddings to generate new representations for my embeddings for the delta KB. And overall, what was pretty exciting about this method is that it was really close to almost a fully incremental performance. I'm able to look just at the delta context data and at the delta entities with this kind of nice little hot swapping operation, although I am going to pay a little bit more cost. The alignment loss is a little more expensive, and so training is going to be a little more expensive than it would be under a completely full incremental update. And this embedding hot swapping, we didn't explore that a lot in the work, but it's a really exciting systems idea to me is what does it mean for downstream systems if my embeddings, I can kind of guarantee that maybe they're all living on the same space. There's again some really interesting systems thing that you could potentially do under this idea of sort of incrementally updating certain subsets of entities. Okay, so now I'm going to quickly highlight a couple results from the work, sort of showing how this update method performs. And we do see overall that this sort of alignment method is better able to maintain performance to the retrained model with a nice speed up compared to some baseline methods. And here I was looking at context incremental, and then I was also looking at a baseline method which did some form of sampling. It was inspired by some work in continuous learning. For those of you familiar, that did a certain style of class stratified sampling. So I sort of adapted it to this framework as well. And again, this is all on these Wikipedia data sets. One of them was on this large Wikipedia corpus, and then one of them was this kind of skewed ablation data set that I mentioned earlier, where only the triangles are in the delta data for the most part. And that's really where that context model starts to fail, is what you can see there. And you see in all cases, our alignment is sort of, again, better able to maintain performance. And you're seeing about a 3 to 6x faster update speed, which is pretty good for these bulk updates. Now, one result I don't have on here, but is worth mentioning, is that what's really nice about this is that for those really frequent updates, the small updates to just the relationships, our alignment method can be up to about 150 times faster than retraining, depending again on the update size. And so you're really able to see how this notion of this kind of alignment update is really good for those small, fast updates, and it's getting a nice speed up there. And so it's kind of better able to handle the different frequencies of updates. Now, I did also explore a little bit at what happens if you chain updates together and look at them incrementally, where in this case, I don't retrain my model at all, and I simply apply sequences of updates. And in this case, I did a sort of 6 sequence update experiment where I had 3 updates and I just repeated the pattern a second time. And so here, I'm assuming you get like 2 small updates. You have like a small update to your types and a small update to your descriptions, and then you get a really big bulk update come in. And then I repeated that process. And here you can see with the alignment model, which is the blue line, that it's actually better able to learn the updated entities, even compared to retraining, but really starts to degrade on these unchanged old entities. And you can think of that as the embedding space is sort of increasingly becoming more and more just sort of distorted as time goes on. What placing embeddings at time t+1, it's not 100% accurate, but then those representations are basically represent your new embedding space at time t+2. And so you get this chain effect where slowly the degradation embedding space starts to hurt performance. Now, as I mentioned earlier, I do want to tease that sample method, the other one in the work, as highlighting that there actually is this really nice trade-off between the two methods. The sample method is struggling a little more on updated entities, but it's actually better able to maintain performance over these unchanged entities, and it really does better with bulk updates. And so you see this really nice trade-off structure where for really small frequent updates, you're better off using this alignment method, and then our sampling method was better for these bulk updates as well. So again, that was all sort of the paper will be out on arXiv very soon. So if people are interested, I encourage you to take a look when that comes out. Now, obviously, this work was still, there's a lot needed here. There's a lot needed here. This was really just a first step in this space. I mean, I think in my mind, clearly there was two big next steps. One of them was understanding and actually thinking about how we can automate the entire process. I sort of gave a lot of proof of concepts that these things could be optimized over, and that there is this really rich trade-off space. But there's a lot to do in terms of actually building and understanding that from also very robustly. To do that, we'd also need a lot of more data sets. I had to craft my own data set over Wikipedia, which worked, but was really wishing that we had, a suite of benchmarks that could help measure this and understand its performance across a lot of different data set types and frequency of updates. And so I think there's kind of a lot of need for benchmark construction as well as understanding how to optimize these things. As I mentioned earlier, this idea of how we can understand the impact on downstream systems, I also think is really exciting. There's this crazy idea in my head of what would you do if you actually never updated your downstream system and only updated your embeddings. Like it's completely opposite of what we do today. And again, maybe a terrible idea, but there actually might be some way you could pull it off if you could sort of guarantee that all of your representations were sort of kind of living all on that same space that the downstream system was first trained on. Like conceivably, you could pull it off. And then you're looking at this interesting trade-off cost of what's faster, retraining my embedding space or retraining the hundreds of downstream systems that interact with these embeddings. Again, I don't know if it could work, but it's kind of something I've been musing about in the back of my head. And so just to give a sort of quick recap before ending and letting time for questions, I feel like I've already taken a little too long here. Again, the whole goal of this whole project was understanding how we could think about this from a view maintenance perspective and how we can incrementally update these models to really capture the different cadences of updates, and understanding that pretty soon in the future we're not going to be able to retrain these models. It's going to get even more expensive, and so we're really going to need to adapt our understanding of how we can manage and maintain these things over time. And I left a couple citations here and contact information if folks are interested. Again, the project was done really like very recently ago, so I'm still working on getting some of the code and data sets released, but they will all be out hopefully in the next 3 to 4 weeks. So that is coming soon. Yeah, and thank you again so much for having me, and happy to take questions now in the time we have left, and happy to stay a few minutes over as well if folks are interested.